All right, guys. This lesson is going over Le Chatelier's principle. So that's 4-3 on your visible learning guide. So Le Chatelier's principle is going to be a key concept moving forward. So it's going to be a concept that's applied in the rest of the units. So it's really important to really understand what's going on with Le Chatelier's principle. So a lot of times, a question might not look like it is a Le Chatelier's principle question, but it really is. So, kind of cutting through, learning how to cut through the fat of a question and figuring out what exactly is being asked. A lot of times, if you come in and you ask me a question about like how do you do this? How do you know what this question is asking about? And I'll go, oh well, think about it. It's a Le Chatelier's principle question. And, oh, okay. So before you start going through and answering a bunch of Le Chatelier's principle questions, make sure you look at the review sheet that I gave you. It's just kind of like a one-page quick guide of the quick points for Le Chatelier's principle, but then you know making sure you go over the guided notes that we went over in class on Le Chatelier's principle, and especially all the little traps that they ask. So really what it comes down to is you have a reaction that's at equilibrium. That means the forward and the reverse reaction are happening at the same rate. So everything, the amounts of everything in the reaction, the reactants and the products are staying constant. But it's not, again, equilibrium isn't a static thing, it's a dynamic thing. So both the forward and the reverse reaction are happening at the same rate. So it looks like everything's just staying the same because the amount of reactant and the amount of product, whenever you measure it, is always the same amount. But it's just because A is becoming B at the same rate B is becoming A. So it looks like it's static, but it's really dynamic. So what Le Chatelier's principle says is, okay, so you have a system that's reached an equilibrium. So the forward and the reverse reaction are at the same rate. And then you change something. You increase the temperature. You decrease the temperature. You put all the reaction stuff in a smaller container. You put all the reaction stuff into a bigger container. You add more of a reactant, or you remove some of the product, or something like that. So you place a stress on the system. So the system has reached equilibrium. You stress it. You change something about what's going on, and what's going to happen is the reaction is going to try to relieve the stress. It's going to try to get back to its normal equilibrium position. And the way that happens is it either will increase the rate of the reverse reaction faster than the forward reaction, or it'll increase the rate of the forward reaction faster than the reverse reaction. Um, so if the forward reaction rate increases more than the reverse reaction, we call that a shift to the right, because everything's shifting towards the products. The forward reaction is increasing in pace. If the reverse reaction increases in rate compared to the forward reaction, we call that a shift left. It shifts back towards the reactants. Okay, so let's get into this lesson. Hopefully, um, it all makes sense. But it's just first figuring out what the stress that you do, the stress that you make on the system, what will that do? Will the reaction shift left or right? And then if it does cause a shift left or right, what will change about the amounts of everything when equilibrium is reestablished? So if the reaction shifts this way, am I going to get more of X, or am I going to get less of X, or I'm going to have the same amount of X? You have to answer kind of questions like that. All right, so let's get into it. All right. So again, this is the kind of the one-page handout to read over for Le Chatelier's principle. But let's get into it, okay? So again, when a system has established an equilibrium, a stress induced on the system will cause the system to react to relieve the stress and reestablish its equilibrium position. Now remember, its equilibrium position is its K value. So as long as you haven't changed the temperature, the K value has to stay the same, the equilibrium constant. So you change something, the reaction is going to try to get back to that K position, that equilibrium position that it has, okay? So, you know, Le Chatelier's principle in a nutshell is if you stress the system will try to relieve the stress. The way I think about it is the system will try to undo what you did. So it's as simple as that. If I add something, it's going to try to take it away. If I remove something, it's going to try to add it. If I increase the pressure, it's going to try to decrease the pressure. If I decrease the pressure, it's going to try to increase the pressure. If I add heat, which means if I increase the temperature, if I add heat, it's going to try to remove heat. If I remove heat, if I cool it down, if I decrease the temperature, if I remove heat, it's going to try to replace the heat that I removed. That's essentially the idea, right? It's going to try to undo what I did. So you have to figure out what is the stress that you did? What did that do? And how does the reaction relieve the stress? Okay. So that's the first question is how does it relieve the stress? Well, the only way it can relieve the stress is, right, if you have this reaction, sorry about this symbol here, it's supposed to be just a double arrow. So you got the forward reaction and you got the reverse reaction, right? So you've reached an equilibrium, which means the rate at which these are becoming that equals the rate at which these are becoming that, right? So the rate of the forward reaction is equal to the rate of the reverse reaction. That means your equilibrium, you're at equilibrium. And then you change something. Well, the only way the reaction can relieve the stress is by either shifting to the right or shifting to the left. So what does that mean? Le Chatelier's principle shift to the right means that the forward reaction rate is increasing faster than the reverse reaction. So to reestablish equilibrium, a shift right means you're consuming more of this and you're gaining more of that. Okay? It doesn't matter what you have on the reactant side and how many things you have on the product side. If you're shifting right, you're losing reactant, you're gaining product. Okay? A shift left means you're increasing the rate of the reverse reaction faster than the forward reaction, okay? So if the reaction, if the stress you cause, if the stress you put onto the reaction causes a shift to the left, that means you're producing more reactant, you're producing more of this, and you're decreasing the amount of product, right? Okay, so really that's the only way the system can adjust, shift right or shift left. So again, shift right means we're increasing the rate of the forward reaction compared to the rate of the reverse reaction. So the forward reaction is happening faster than the reverse reaction. So reactants are being consumed faster than products are being consumed, if that makes sense. Okay. And a shift left means the opposite. Products are being consumed. So the reverse reaction, so these are being consumed faster than these are being consumed. All right. Okay. So how can you cause a shift? What are the stresses that you can do? Okay. The first stress is just add more stuff. So add more reactant, add more product. Okay. The second thing you can do is remove some stuff. You could remove some reactant or remove product. Okay. So let's talk about what happens when you add a reactant or add a product. So the other key thing to understand is only things that are in the aqueous state or the gaseous state, if you add or remove, will cause a shift. If something's in the solid state or the liquid state, you're not going to cause a shift. Okay, you're not going to cause a shift. There are a few exceptions to that. Like if you're talking about the solubility of the salt, if you add more water, obviously more salt can dissolve. Okay, but adding water decreases the concentration of things. So like decreasing the concentration of something is like removing it. So the reaction is trying to replace it. All right. So if you add, so it's pretty simple. If you add something, it's going to shift away. So if you add reactant, it's going to shift towards the product. So it's going to shift right. If you add product, it's going to shift away from the product. So it's going to shift left. Okay. So again, it's trying to undo what you did. I added it, so it tries to consume it. So how does a reaction consume reactants? It shifts to the right. How does a reaction consume, get rid of product? It shifts to the left. Okay. If you remove something, again, go back to Le Chatelier's principle. There's just the overall idea is if I change something, if I do something, the reaction tries to undo it. So if I remove something, the reaction is going to try to replace it. So whatever I remove, the reaction is going to shift towards that thing. So if I remove reactant, it's going to shift towards the reactant. So it's going to shift left. But if I remove some product, it's going to shift right. Okay. The other stress that you can add or remove something. The other thing is increasing or decreasing the temperature. But the way you should interpret that is like adding or removing. Increasing the temperature is like adding heat. So what happens if I add heat? All right. Increasing the temperature is the same thing as adding heat. Okay. And decreasing the temperature is removing heat. Cooling something down, decreasing this temperature is removing heat. So again, if you go back to the idea that it's just going to undo what I did, if I add heat, it needs to remove heat. If I remove heat, the reaction needs to add heat, right? It's just trying to undo what I did. Okay, so to determine which way you're going to shift, you need to know whether the reaction is exothermic or endothermic. Okay, so remember, if it's exothermic reaction, you want to think of heat. Heat is a product. So heat is on the product side if you have an exothermic reaction. So if you know you have an exothermic reaction, heat's a product. If you add heat, it's going to shift away from heat, which is on the product side. So it's going to shift towards the left. Okay. So if you increase the temperature of an exothermic reaction, you're going to cause it to shift left. Okay. If you cool it down, if you decrease the temperature, that means if you remove heat, it's going to try to replace the heat by producing heat. Well, heat is a product if it's an exothermic reaction. So if it's an exothermic reaction and heat is a product, if you remove heat, if you cool it down, it's going to shift towards the right, towards the products to try to replace the heat that you removed. Okay. So another way to think about this is exothermic reactions become more favorable as you lower the temperature, right? And that should make sense. Like think of an exothermic process. How about water freezing? Liquid water freezing into ice. You can freeze more ice, right? You can freeze more water at lower temperatures, right? As you lower the temperature, the favorability of freezing water increases. But as you increase the temperature, the favorability of freezing water decreases, right? So for exothermic reactions, they become more favored. The forward reaction becomes more favored at low temperatures. The reverse reaction becomes less favored at low temperatures. Okay. Okay, and so the opposite's true for endothermic. So if you're endothermic, you need to think of heat as a reactant. So if you add heat, if you increase the temperature, you're adding a reactant. It's going to shift towards the right. It's going to try to get rid of the heat you added by consuming it. Okay. If you decrease the temperature, you're removing heat. It's going to shift back towards where heat is. But in this case, for endothermic reactions, heat is on the reactant side. So removing heat is going to cause it to shift towards the reactant. So it's going to cause it to shift left. Okay. So endothermic reactions are more favorable at high temperatures. Exothermic reactions are more favorable at low temperatures. Okay, that's an important thing to understand moving forward. Okay, right? Think ice melting into water. When does this become? This is an endothermic process. When does this become more favorable? At high temperatures. As you increase the temperature, you should be thinking heat is a reactant because you know that ice melting is an endothermic process. Okay, so if you add heat, it's going to shift away from heat. If I remove heat, if I cool it down, it's going to shift towards heat. Okay, so that's what we're saying. Okay, and so the last stress that you're going to, look out for Le Chatelier's principle that can cause a shift. So we can add or remove things, and that's reactants, products. We can add or remove, and now we can think of heat as either a reactant or a product, depending on if it's endothermic or exothermic. And so if you add or remove, it's going to just, if you add something, it shifts away. If you remove something, it shifts towards. But now you're thinking about pressure, okay? And a lot of times you're not going to be told that you've increased or decreased the pressure. What you're going to be told is that you decreased or increased the volume. So you have to remember that pressure and volume are inversely proportional. So let's imagine you have a reaction that just a bunch of gas particles going on. So the reactants are gases, the products are gases. So in your reaction container, you just have a bunch of gas particles. If you increase the pressure, the reaction is going to try to decrease the pressure. If you decrease the pressure, the reaction is going to try to increase the pressure. But really what's going to end up happening is how do you decrease the pressure? You increase the volume. So you're going to increase the volume of your reaction container, which you should know decreases the pressure. Okay. Or you're going to decrease the volume of your reaction container. And if you decrease the volume, you should understand that increases the pressure. Okay. So if you increase the pressure, the reaction will try to decrease the pressure. If you decrease the pressure, the reaction will try to increase the pressure. Okay. All right. So how does a reaction increase or decrease the pressure? It has to shift to the side. So if you want to, if the reaction wants to increase the pressure because you decrease the pressure, it's going to shift to the side with more gas particles. Okay. So if you decrease the pressure by increasing the volume, so let's say we increase the volume, you have to say to yourself, okay, I increased the volume. That means the pressure is going to go down. So the reaction is going to try to bring the pressure back up to the equilibrium position. And it's going to shift to the side with more gas particles. So that could be left, it could be right. It just depends on the reaction. So if there's more gas particles on the product side, it would shift towards the products. If there's more gas particles on the reactant side, it would shift towards the reactants. Okay? So it's going to shift to more gas particles. And then if you increase the pressure by decreasing the volume, the reaction is going to try to bring the pressure back down by shifting to the side with less moles of gas. Okay? If there's equal gas particles on each side of the equation, then there won't be a shift. The reaction can't relieve the stress at that point. Okay? All right, so let's do a couple practice problems here. All right, so here's our reaction. And look, they gave us the delta H. So the first thing we should understand is, okay, that delta H was a negative. All right. That means I should go plus heat. Oops, not G, plus heat. Okay. And I know I can add heat on my product side because delta H was negative. It's telling me it's an exothermic reaction. So now I know where heat is. Okay. So the following reaction was established at equilibrium at 25 degrees Celsius. Which way will the reaction shift to reestablish equilibrium when the following stresses are placed upon it? So this one we're just answering, will it shift to the left or will it shift to the right? More hydrogen gas is placed in the container. So we add more hydrogen, it's going to shift towards the right. Okay? Some ammonia is removed. We remove some of this ammonia, it's going to shift towards the right to replace the ammonia. Okay? Some nitrogen is removed. All right, so we remove some nitrogen, the reaction is going to shift to the left to replace the nitrogen that I removed. The temperature is lowered to 15 degrees Celsius. All right, well, let's think about it. Heat's on this side. Lowering the temperature is removing heat. So if I remove heat, the reaction is going to shift towards heat. So it's going to shift to the right in this case. And that's because I put heat on this side of the equation because the delta H was negative. Okay. All right, how about number 5? The container is compressed. Okay, so that means we made the volume smaller. That's going to increase the pressure. If I increase the pressure, okay, the reaction is going to try to decrease the pressure. In that case, it's going to shift towards the right because there's only 2 gas particles here versus 4 gas particles here. So me decreasing the volume, I know that that increased the pressure. For this reaction, it's going to shift towards the right because there's less gas particles on this side of the equation. That's going to bring the pressure back down. Okay. All right, so let's look at this one. Magnesium sulfate dissolves in water according to the equation above. The process has reached an equilibrium at 25 degrees Celsius. What direction will the reaction shift when the following stresses are placed on the system? So again, we're just saying shift left or right, but we got to be a little bit careful now because we have a solid in here. Remember, a solid is not a part of the equilibrium position. If we wrote the equilibrium expression for this reaction, we would not include this in that equilibrium position, okay? The other thing, delta H is a positive value. That means heat is a reactant, not het. So I can throw heat on this side of the equation. All right, so more solid magnesium sulfate is introduced to the container. Okay, this is a trick question, no shift. Okay, think about it. When a salt dissolving in water has reached equilibrium, that means the solution is saturated. That means you can't dissolve any more of that salt unless you added more water. Okay, so all we did was add more salt to the container. More salt's not going to dissolve, so that's a trick one, no shift. Remember, if you add or remove solid or liquid, liquid would be a different thing if you added liquid water here, because if you added liquid water, then the reaction would shift to the right because these concentrations would go down. It would be like removing these. All right, but if you add a solid, it doesn't cause a shift. All right, so that's one of the Chatelier's traps. Don't fall for it. All right. All right, the mixture is heated to 50 degrees Celsius. So if I heat up a container, I'm adding heat, okay, or a reaction, I'm adding heat. Heat's a reactant. How do I know heat's a reactant? Because delta H was positive. So now adding heat is going to cause it to shift to the right. So this would be shift to the right. Right, and that would produce more of the aqueous ions there. All right, now here is one that I really want us to understand. Adding some barium nitrate. Okay, so first I'm just going to let you know that this causes a shift right. Okay. But how? Barium nitrate is not a part of this reaction. Okay, this is where we have to start thinking about things a little bit deeper. All right. They're not going to just say, hey, you removed sulfate. If I said, hey, you removed sulfate, or the amount of sulfate decreased, then you would know, oh, okay, it's going to shift to replace the sulfate. But the question is, how do you remove sulfate? You can't just sit there and handpick sulfate ions out of your solution, right? How do you do it? Well, barium nitrate's very soluble. How do you know? Well, because it's a nitrate. Okay. Well, what about barium ions coming in contact with sulfate ions? Barium sulfate is very insoluble. So adding barium nitrate to this solution, barium sulfate is going to precipitate. So sulfate is going to precipitate out of solution. So you're removing sulfate from solution, so the reaction shifts to the right to replace the sulfate that you're removing. So this is adding some barium nitrate is the same thing as, hey, I removed some sulfate, right? If I had just come out and said, hey, I removed sulfate ions, you would have said, oh, it shifts to the right. It replaces the sulfate ions. Well, this is how you do it. How do you remove some sulfate ions? Add some barium, okay? All right, so here is another reaction. All right, and so notice that delta H is a positive. So what does that mean? It means heat is a reactant. So I can add heat to this side. Another thing to note is two gas particles. So increasing or decreasing the volume, which would increase or decrease the pressure, will not cause a shift because I have equal moles of gas on each side. So that's another thing to kind of look at, okay? But now let's look at this question. This isn't asking which way that will the reaction shift. It's asking after the shift occurs, what happens to the partial pressure of H2? Does the partial pressure of H2 increase, decrease, or remain the same? And then it's asking the value of the equilibrium constant. Let's call it Kp, okay? Does it increase or decrease or remain the same? So the first thing I would say is understand the only time that the K value changes is if temperature changes, okay? So number 6 is the only time where the value of K will change. So 1, 2, 3, 4, 5, and 7. The second part of the question, K will remain the same. 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 The only time K will change is number 6. All right. Okay. So more HBr is added. So if we add more HBr, the reaction is going to shift to the right, producing more H2. So if you have more H2 gas, when equilibrium gets reestablished, the partial pressure of H2 will increase. So we'll say H2 increases, Kp stays the same. Okay. More bromine is added. So if I add bromine, the reaction is going to shift to the left. That's going to consume some H2. So when when equilibrium gets reestablished, you'll have less H2. So the partial pressure of H2 decreases, but Kp stays the same. H2 is added. Now this is tricky, okay? And I'll show you why. I add H2, that's going to cause a shift to the left. And that's going to consume some of the H2 and some of the Br, okay? And the Br that's there, the Br2, okay? But let's answer the question. When equilibrium is established, H2 is actually going to increase. The partial pressure of H2 increases, even though it shifted away from H2. It shifted away and some of the H2 is consumed, okay? But we'll get to why. But the partial pressure of H2 when equilibrium gets reestablished increases, and Kp stays the same. But let's understand. Let's understand what's going on here. Okay. Kp equals this ratio, right? The partial pressure of H2 times the partial pressure of Br2 over the partial pressure of HBr squared, right? Let's think about it. You add H2, the reaction shifts this way. So the amount of this increases. And you know that the amount of this absolutely decreases. So let's think about it. K can't change, right? K has to stay the same. So you know that this value goes down and this value goes up. So the only way to maintain a constant K value is if the partial pressure of H2 actually increased, okay? So yeah, you added H2 and it shifted away from H2 to consume some of that H2. But when equilibrium gets reestablished, you end up with more H2 than what you had before you caused the stress. Okay, so that's a Le Chatelier's principle trick. Whatever you add, it's going to shift away from that thing. But when equilibrium is reestablished, you always end up with more of what you added. You always end up with more of what you added when equilibrium gets reestablished. You want to think about that, all right? All right, some Br2 is removed. So I remove Br2. The reaction shifts this way to replace that Br2, but in doing so, it produces more H2. So H2, the partial pressure of H2 increases. Kp stays the same. Okay. Some H2 is removed. I remove H2. The reaction shifts this way to replace some of the H2. It also produces more Br2. So H2 is going to actually decrease the partial pressure, even though we're shifting towards H2. The partial pressure of H2 when equilibrium gets reestablished is going to actually decrease a little bit. Kp stays the same. But why is that? Because now the reaction shifted towards the right. You know that this number absolutely increased. You know that this number absolutely decreased. So to maintain a constant K, then you know that this number also has to decrease. Okay. All right. The reaction is heated. So in this case, you heat the reaction vessel. the reaction is going to shift towards the right, producing more H2, and the H2 gas is going to be at a higher temperature. So 2 reasons why the partial pressure of H2 increases. You have more H2 particles, and the particles are moving faster because you heated it up. And because this is an endothermic reaction, the reaction becomes more favorable at higher temperatures. So that means at the higher temperature, Kp will increase. You'll have more products and less reactants. Okay, and that's because a shift to the right increases the products, decreases the reactants, and if K is a ratio of products over reactants, Kp is going to increase that. K always increases as temperature increases for endothermic reactions. Okay, that's the opposite for exothermic reactions. So the volume of the container is doubled. All right, so here's where this is tricky. There wouldn't be a shift because you have equal moles of gas, right? Okay, but be careful. There is no shift. There's no Le Chatelier's principle shift, but that means the partial pressure of H2 would decrease. Why? Because there was no shift, so the number of H2 particles in the container stays the same, but now it's in a bigger space. So you have a bigger volume, same number of particles moving at the same speed because the temperature didn't change. So partial pressure decreases, and K stays the same. All right. So just some things. You are not just trying to answer if the reaction will shift left or right or no shift. Understand what getting back to equilibrium position means. Most of the time that means getting back to the K value. The only time the K value changes is if temperature changes. Okay. You always end up with more of what you added, and you always end up with less of what you removed. You always end up less of what you removed when equilibrium gets reestablished. Okay. The Le Chatelier's tricks, adding or removing solid or liquid doesn't cause a shift. Catalysts don't affect equilibrium. A catalyst increases the rate of reaction, so it increases how fast you get to equilibrium, but a catalyst doesn't change the equilibrium position. If you have equal moles of gas on each side, then there won't be a shift if pressure changes. And one other thing that I didn't mention, but sometimes this is what they like to do this type of question a long time ago, but I haven't seen it on any of the recent tests. But if you add a lot of inert gas, like let's say we went back to this reaction and we added a bunch of helium, like 50 moles of helium were added to the container. Yeah, that's going to increase the overall pressure, but it doesn't change the partial pressures of any of the gases involved in the reaction, so it doesn't cause a shift. So increasing the pressure by adding a lot of inert gas does not cause a shift. All right, so really, if you're looking for which way the reaction is going to shift if you increase or decrease the pressure, it's really not by adding some gas that's not involved in the reaction. It's about increasing or decreasing the volume. All right. Okay, so hopefully that gives you a better understanding of Le Chatelier's principle. And it was one of the longer videos, so I'll call it a day. Have a good one.